Imagine if everything we thought we knew about Earth's water was just the tip of the iceberg, because beneath our feet, there could be 3 times more water than all the oceans combined. This astonishing possibility, once the stuff of science fiction and the visionary writings of Jules Verne, is now backed by compelling scientific evidence. But here's where it gets controversial. This water isn't flowing in underground lakes or rivers. It's locked away deep within the minerals of Earth's mantle, hidden from view and challenging our traditional understanding of the planet's water cycle. The journey to this revelation began years ago, with geologists suspecting that vast amounts of water might be stored far below the surface. In 2014, a pivotal study led by geophysicist Steve Jacobson from Northwestern University and seismologist Brandon Schmont at the University of New Mexico provided strong clues. Published in the prestigious journal Science, their research uncovered unusual seismic signals beneath North America that hinted at a hidden water cycle operating hundreds of kilometers underground. These seismic anomalies suggested that water was influencing the mantle's properties in ways previously unimagined. Yet, it wasn't until 2022 that mineralogical proof emerged, thanks to a remarkable diamond discovered in Botswana. Today, the evidence supporting the concept of a deep water Earth is more convincing than ever. This discovery has profound implications, potentially transforming how we understand not only tectonic movements and volcanic eruptions, but also the long-term climate regulation of our planet. For example, volcanic activity, which shapes landscapes and affects atmospheric conditions, may be directly influenced by this deep reservoir of water. So, how exactly does this hidden water exist? The key lies in a mineral called ringwoodite, a high-pressure variant of olivine found in the mantle's transition zone, located roughly 410 to 660 kilometers beneath the surface. Under the crushing pressures and scorching temperatures exceeding 2,000 degrees Fahrenheit, about 1,100 degrees Celsius, ringwoodite behaves like a sponge, not soaking up liquid water, but trapping water molecules as hydroxyl ions within its crystal lattice. This means the water is chemically bound inside the mineral structure, rather than existing as free liquid or vapor. Jacobson's team recreated these extreme conditions in the lab using sophisticated high-pressure devices known as diamond anvil cells. Their experiments showed that ringwoodite can hold approximately 1% of its weight in water. While that might sound minimal, when multiplied by the enormous volume of rock in the mantle transition zone, it translates into an immense quantity of water. Schmant's seismic studies complemented this finding. Using the U.S. array, a vast network of over 2,000 seismic sensors spread across the United States, his team detected signs of partial melting deep in the mantle. This melting is a hallmark of water being released from minerals as they descend deeper into Earth's interior. The only known mechanism to explain this phenomenon is dehydration melting, where hydrated minerals like ringwoodite lose their trapped water under intense heat and pressure. The breakthrough came in 2022 with the discovery of a diamond from Botswana's Korowe mine containing ringwoodite inclusions. Published in Nature Geoscience, this study revealed that the diamond encapsulated multiple hydrated minerals, providing direct, tangible proof that water exists at depths around 660 kilometers. As co-author Fabrizio Nestola explained, the diamond serves as a geological time capsule, preserving minerals from deep within Earth that would otherwise break down before reaching the surface. What's even more fascinating is that these hydrated mineral inclusions weren't isolated anomalies. Instead, they indicated a widespread, water-rich environment within the mantle transition zone, suggesting that this region acts as a massive reservoir of water. But this water isn't like an underground ocean. It's intricately woven into the very fabric of Earth's minerals. This leads us to the concept of a deep water cycle, a process that operates on geological timescales and is fundamentally different from the familiar surface water cycle of evaporation, condensation, and precipitation. Here, water is transported deep into the mantle, when oceanic plates subduct at tectonic boundaries, carrying water-rich sediments and rocks with them. Some of this water becomes trapped in minerals like ringwoodite, while some is eventually released back to the surface through volcanic eruptions, influencing everything from earthquake dynamics to volcanic activity. As Schmant eloquently put it in 2014, geological processes on Earth's surface are an expression of what's going on inside the planet, out of our sight. We are finally seeing evidence for a whole Earth water cycle. This perspective challenges the long-held view that Earth's hydrosphere is a closed system confined to the surface and atmosphere. Instead, it suggests a dynamic exchange between surface water and deep mantle reservoirs, potentially acting as a natural buffer that stabilizes Earth's climate over millions of years. But here's the part most people miss. If this deep water cycle is so crucial, why hasn't it been more widely accepted until recently? Could it be that our traditional geological models have underestimated the complexity of Earth's interior? And what does this mean for our understanding of other planets? Might they also harbor hidden water reservoirs deep beneath their surfaces? These questions open the door to lively debate. Do you think the idea of a deep water Earth will revolutionize geology and climate science? Or is it an overinterpretation of limited data? Share your thoughts and join the conversation, because the story of Earth's hidden water is far from over.